Thank you. Welcome, everyone. This is our 9th talk in the series, I believe. And İlker from ODTÜ, from Middle East Technical University, is going to talk today about higher structures in physics. He's a PhD student in ODTÜ, METÜ, and he is in the job market if anyone is interested in giving him a postdoc position. So, İlker, we are listening to you.
Thank you very much, and thank you for having me here today, actually, and thank you for this kind introduction. I'm actually glad to be here, part of this event. So thanks again. Today, actually, so this is a kind of an overview, right? So this is a kind of an overview of higher structures in physics, basically, and therefore we will basically start with. In section 1, we will start with using, using standard language. So we will present the standard way of describing things, basically. And maybe I should mention this. In this talk, we will focus on basically classical part of the story. The quantum part of the story is interesting, okay? But in this talk, we will focus on basically formulation of classical field theories and especially gauge theories and gravity. And in this second part of the talk, on the other hand, we will introduce a new language, basically new perspective. And basically, we will use the language of derived algebraic geometry. And we will study basics of that theory. And in this third part, the last section, we will combine those ideas. We will revisit part 1, and by using this new language, we will actually, so we shall see this new language in action, basically. And and also you may ask why, why we need this? So what are the benefits of doing this new, or using this new language? So basically, we shall discuss those topics, okay? Fine. So the first one, so let me start with the definition of a classical field theory. Of course, the definitions will be given informally, okay, but the basic data we need, okay? So the definition. So actually, a classical field theory, and basically it consists of the following data. So we need a base manifold, of course, and we have a kind of a space of fields, Fm, let me denote by Fm, and a kind of a certain function, in general it is called an action functional, and we have a certain group which encodes the symmetries of the system. So this M is your base manifold. So this Fm is actually about a choice of a sheaf, actually, more formally speaking. So you have a sheaf on M, and this Fm is just a section, space of sections of that sheaf. Okay, so these are the space of fields. So the space of fields of the theory. Okay, and this S is a kind of a smooth function on the space of fields. Okay, with some field K. In general, it's a complex number or reals. And G is your symmetry group, if you like. Very roughly speaking. But of course, this is not the whole story. So we really wish to understand the dynamics of the system. Okay, so we really wish to understand, so to encode the dynamics of the system. Actually, we really need to study the critical locus of that thing. This action functional. So the critical S. So in general, of course, this is a kind of a moduli space at the end of the day. And we really are interested in specific fields, whatever the theory is, such that basically we have this kind of condition. So the critical locus and quotient out by your symmetry group. And this is called the critical locus. And if you look at carefully, this condition tells us or gives actually the system of differential equations. These are gives or defines the fields equation of the system, of the theory. Okay, fields equation. And sometimes this is called Euler-Lagrange equations. Okay, Euler-Lagrange equation. And actually this formalism is called sometimes, if you like, Lagrangian formalism. Okay. Okay, so this is more or less the basic data, okay, very roughly speaking. When you define a theory, you need a kind of a framework like this. So for instance, so let's see some examples. For instance, just consider the usual classical free particle in action. I mean, just consider a free particle of mass m. So you have a path like this, and you have an interval, let's say 0, 1. So this is your image, and this is Rn. Okay, so we try to describe the motion of a free particle in Rn, if you like, by using this data, by specifying this specific data. Okay, so the data is actually the data here specified like this. So Rm now is just the unit interval. Our sheaf is just a free sheaf, or if you like, usual trivial vector bundle. It's just a free sheaf. And what else? Space of fields turns out to be just, you know, the regular functions, right? In the setup are just, you know, m to Rn, smooth maps. But m is just a unit interval, therefore the elements are just path, right? A path in Rn. So this is your fields in that theory. And what else? You need to specify the action functional, right? So S, let's say, acts on Q. So in general, we have, it's given like an integral like this, Q dot squared divided by 2 and VQ. VQ, let's say a certain function. So V is just a certain function on Rn, real value. In general, this is called, let's say, potential. Okay, for those who are familiar with this discussion, this is the usual, right, in classical mechanics, mv squared minus potential term. So the expectation is somehow we need to end up with Newton's theory, right? And this is the case actually. Just look at the critical locus of that thing and the Euler-Lagrange equations. If you analyze it, you end up with this equation, minus gradient VQ. And this looks familiar. This is just, you know, this Newton's F equals ma. Okay, so this is one way of defining a theory. And of course, the symmetry group is the isometric group of Rn, right? The rigid motions. Okay, so this is one example. And another example is, let's say, another theory. For instance, Einstein Gravity in a very specific setup. Einstein's gravity in a little bit unrealistic dimension, but 2 + 1 dimension, and in a vacuum case. I mean, it's not important at this stage, so let's see. This is lambda is just cosmological constant. Anyway, so we have, let's say, a manifold like this. Our base manifold, it is chosen like this, okay, in this very specific setup, Rn. So this sigma g is just a Riemann surface of genus greater than 1, okay, for some reason. I mean, I'm not going to that much detail, but this is our example, okay. So let's consider some open neighborhood here. So U is just open in M. Now our sheaf is a kind of a sheaf of matrix on M. Okay, so this curly F will be a sheaf of matrix. In general, maybe I should say the pseudo-Riemannian matrix or Lorentzian matrix on M. Okay, and then therefore your space of fields will be just the space of pseudo-Riemannian or Lorentzian matrix on M. Okay, this is your space of fields. In general, these are denoted like G. Okay, so therefore we really interested in metrics or the geometry, right, defined by the metric G. And fine, of course, we should specify the other data. In general, S will be given as the usual Einstein Hilbert action. Okay, it is given like this. So we have some coefficients here. G, M. So it's a three-dimensional, remember. So we have this volume elements, right? And R is the Ricci scalar from Riemannian geometry, and this part is just a determinant. Okay, so if you analyze this function or functional, if you like, and your critical points or the corresponding Euler-Lagrange equations turns out to be the usual famous Einstein's fields equation, right, in local coordinates. Okay, so fine. And if you look at carefully, and the space of space of interest turns out to be moduli space of flat matrix, okay, Ricci flat. And then here maybe you may ask, what is G? Our group is just a diffeomorphism group. And it acts on Fm by pulling back. So you just pull back matrix by pulling back. Okay, maybe if you go back here, if you have some diffeomorphism here, phi, you just pull back this metric. Okay, this gives you another metric. Fine, and then in this setup, the space of interest is the space of interest will be the moduli space of Ricci flat pseudo Riemannian matrix on M. So we really wish to understand this space. Okay, so this is the idea. Fine, maybe the final example for this section is another famous theory, SU2 Chern-Simons gauge theory on M, but M is chosen in a very specific way, S3, okay, 3 sphere. I mean, for those who are familiar with this theory, this is actually really famous. Remember, this is, for example, related to topological quantum field theories or Witten's knot invariance, right? So introduced end of 80s, if you remember. And also it is related to infinite dimensional Morse theory. So this theory is really crucial. So let's try to formalize this theory with this, the above language. Now here, so what is it? So we need to specify our space of fields. This is just connections, oops, okay, connection one form, but Lie algebra valued. Okay, so the Lie algebra valued connection one forms your fields basically. And sheaf is, you know, this tangent, cotangent bundle. And the action functional, on the other hand, so the S acts on A. So this is, again, the famous Chern-Simons action functional, okay? Trace, okay, something like this. Okay, and fine. What else we need? When you analyze this action functional and look at its critical points and blah, blah, and same tricks, the corresponding Euler-Lagrange equations turns out to be this. A wedge A is 0. And this term is actually so-called, in general, the curvature 2 form. This is the curvature two form, maybe it's a little bit unfortunate notation, don't confuse with Fm. And then the space of interest here, actually the moduli space of flat, okay, flat G, I mean this SU2 connections on M. This is your space of interest basically. And maybe also we have some extra data. What about symmetries? In general, the action of this symmetry group given like this. So G's are in general called gauge transformations. And it acts in a certain way, okay? Something like this. These are standards, standard notions, by the way. But the important thing is actually we will come to that point later. Just remember, we should remember the gauge transformations and the connections, okay? In here, for instance, if you have a connection, for instance, a connection on that manifold M, and actually two connections are related to each other, right? And we say that they are the same if they are related to each other by a gauge transformation, right? Therefore, we say that A prime and A are the same if there exists a gauge transformation in G such that, okay, A prime is A dot G. So this is really important later, okay? We will come back to that later. So this is more or less the idea. So these are standard examples. Now we really wish to introduce a new, maybe not new, but a natural framework to record this data in a more effective way. Okay, so this brings us the second part of the talk, basically. So the next one, the moduli theory and higher spaces. So the key point is actually the following. So remember, actually, in part one, we used the word moduli many times, right? So this is the reason the moduli theory and the corresponding moduli spaces is actually the important part. Now let's see, what is the idea here? What is a moduli problem? Very roughly speaking, informally speaking, if you like, this is a problem of constructing a classifying space for objects up to their intrinsic symmetries, right? So this is more or less, I mean, the slogan is, if you like, this is about classification of objects. Fine, but at the end of the day, how can we capture this information? So for a moduli problem, we really wish to find, so actually we really, we are seeking for a specific space. So seek for a specific space, which is called a moduli space. Let's say M, having those properties. In general, it has two important features, basically. The first feature is, right, so it should parameterize what you want to parameterize, right? So it's a parameter space. It is a parameter space, meaning that there must be a kind of a one-to-one correspondence between the points of M and the isomorphism classes of objects so you wish to classify, right? So it's a parameter space. And if you have only this property, not the second one that I didn't mention yet, if you only have this property, this is called coarse moduli space, okay? But in general, we are looking for a space fine enough to classify not only, I mean, we really wish to want somehow, how should I say it? A space fine enough to classify families of objects, not the objects itself, but the families of objects. So therefore, the second property should be, this should be somehow sensitive enough to distinguish families. families of objects. Okay, so if you have this property, so these two, if you have a moduli space satisfying this property, this is called actually, so just a second, this is called a fine moduli space. Okay, but in general we have a problem, so it is really hard to find moduli space. And actually maybe a short comment here, this really equal to the existence of a universal classifying object. In M. What does it mean? All other objects parameterized by M can also be reconstructed by using this special universal object. But the problem is, in general, we have an existence problem. Okay, so for instance, let me give you an example. Actually, a very familiar classification problem, classification of Riemann surfaces or elliptic curves. So remember, in classification of elliptic curves, so Riemann surfaces, for instance, remember the fundamental domain can be given like this. So you have an upper half plane, right, divided by the action of the group PSL to Z, right? Remember, so we end up the picture like this. So very roughly speaking, right? This is 1/2 minus 1 1/2. This, remember, this was, I mean, it's a bad picture, but this is more or less our fundamental region. And remember, for each complex number here, you have a Riemann surface up to homothetia and stuff. And remember, so for each tau here, you assign a Riemann surface like this, right? This lambda here, just a lattice of rank 2. And this thing actually a coarse moduli space. So lambda is a coarse moduli space, not fine, but not fine, which means that it is not able to, I mean, it's not good enough to distinguish families of elliptic curves. And this is because, I mean, due to the existence of non-trivial automorphisms in general. So, but not fine, okay? And this is in general due to the existence of non-trivial automorphisms. Okay, very roughly speaking, okay? If you like, we can discuss detail later. So it's therefore somehow we have kind of an existence problem, and equivalently using category theory, we can formalize this problem in the following way. So the existence problem maybe as a lemma here. So the existence of a fine moduli space, let's say M, this thing corresponds to the representability of the corresponding moduli functor. Remember, so we can really define a functor from C op the sets. So this is your moduli functor, and if this is representable, meaning f is given, I mean, this is isomorphic, if you like, as a Yoneda functor, right? This is just the home M for some M in your category. Okay. So maybe as a slight remark here for those who are not familiar with this representability business, actually there are some key ideas. First of all, Yoneda embedding, right? So there exists so-called Yoneda embedding, which will be important later on. And for any objects in a category, for instance, a category of schemes, if you like, you can really consider as a functor. Okay, this is called the functor of points approach. So for each object in U, this defines a functor HU. Okay, this is just a C op to sets, a kind of a functor. So for each Y, this is given like at least on objects maps from Y to U. Okay, and the important lemma, remember the Yoneda lemma says that basically this H is fully faithful, or if you like, it's a kind of an injective, okay? Which means that if you know all morphisms into U, okay, and you can uniquely define U, okay? So H is fully faithful. This means that more or less injective. Therefore, knowing HU uniquely determines U, okay? So this will be really important soon. But the problem is, this is not a kind of a surjective. Therefore, not all functors from C op to sets are given in the form of HU. When it does, we call it representable, okay? But not essentially surjective. Therefore, this motivates the definition of a representability. When it does, we call it representable. Therefore, similar problem here. So similar kind of existence problem we have here. So let's see. We will see that higher structures and the higher spaces resolve this problem. This is the reason why we use kind of stacky language and derived algebraic geometry. Fine. Let's use this Yoneda embedding in a more effective way. Just a second. Okay, actually using Yoneda embedding, actually certain algebra geometric objects can be formalized by using this functorial perspective. Okay, so we have a functorial perspective. This part is really important, so perspective. So thanks to this Yoneda lemma, we have the following observation. Here is the observation. Consider schemes, right? The usual scheme. Remember, schemes can be seen as a kind of a functor from the category of commutative K-algebras to sets, category of sets. So this is basically can be seen as a definition of a scheme. Of course, this is a kind of a pre-sheaf, and we have a kind of a local to global condition. Then you have a sheaf. So just we use schemes as a sheaf of sets from, you know, this category of commutative K-algebras to sets. Fine. And actually, we can play with this diagram. Actually, we can play with this. So like this, so we can play with the source category and the target category in the following way. So instead of sets, let's move to groupoids. Okay, so but now this is just a two category of groupoids. So this is a kind of a category of categories like an statement. So the groupoids are just the categories in which all morphisms are isomorphisms. Okay, and the collection of groupoids actually do not form a category. So you need a more refined notion. I mean, the notion of a category is basically too naive to capture the higher structures. But now you have higher structures because now you have two morphisms, right? In case of groupoids. So you have objects, these are categories, and you have one more morphisms, these are functors, and you have two morphisms, these are natural transformations, okay? And therefore, we have higher category to capture this object, the properties of this object. And also we can define, oops, sorry. So simplicial sets. This is called the infinite category of simplicial sets. Why infinite category? Because now you have more higher structures. Now you are allowed to, you have notions like morphisms between morphisms, or you have notions like morphisms between morphisms, between morphisms, and like this, okay? And so let me write it down. So here's the idea. So the simplicial sets, just remember your, you know, the usual objects in algebraic topology. Just consider them like a collection of sets, okay, xn, and xn's are the sets. This is important. This is set of n simplices. Okay, so let's see. So let me try to explain what's going on. So when you move in this direction, basically, when you move in this direction, what you have? You have non-trivial higher structures. Non-trivial higher morphisms. Okay? And you have notions like morphisms between morphisms, or morphisms between morphisms between morphisms, and the story goes like this. And therefore somehow you have infinite tower of equivalences. So if you have higher symmetries in your theory, you can capture the data by using this structure. Okay? And as I said, so more or less the level of abstraction is changing, therefore we need to employ higher category. So employ higher category theory. And maybe the nice observation is that maybe as our slogan, this will be crucial. So basically the different layers of the simplicial structure okay, encodes basically different levels of symmetries. Okay, different levels of symmetries. And maybe the intuitive picture is like this. Maybe you will understand better. This procedure is called the simplicial enrichment sometimes. Just consider like this. For instance, your objects are like vertices. Okay, let's say A and B. Therefore, usual zero simplices corresponds to your objects. And you can attach, right? Recall the algebraic topology, you can attach edges, right? And the edges are your maps. So x1s, one cells or one simplices, whatever, corresponds to usual one morphisms. Okay, let's say F and G. And now you can attach two cells. So you may discuss the maps between two maps. So let's say this is phi. So this is x2. This corresponds to two morphisms, if you like. Or you may have further symmetries. For instance, you have another pair of one morphisms, F prime, G prime, and you may have maps between these two, phi prime. And you may ask for maps between these two. Okay, just like attaching three cell, right, in your simplicial structure. Therefore, this corresponds to three morphisms. And story goes like this. So this is just one part of the story. And if you go back, remember, we just play with the target category here. And actually, you can play with the source category. Right? Remember, so if you have a commutative K algebra here, so any commutative K algebra can be seen like this. right? With D, D is 0. So any commutative algebra can be seen as a CDGA. So what does it mean? Commutative differential graded K algebra. Therefore, there is a natural embedding here to the category of CDGAs. For some reasons, we need some negative parts. And fine. So we have a kind of a diagram here. What is changing here? We just change our local model. So what we are doing when we move in this direction, we just basically change the local algebraic model. So what does it mean? So let's complete the diagram and you will understand what's going on. This kind of assignment now will be called stacks. Okay, remember this is a scheme, this is a stack. So these parts will be called higher stacks. Oops, higher stacks. And this part is called the derived stacks. Okay, and actually remember, in the usual case, remember the affine scheme will be given just a spec of A, right? This is your affine scheme, but now here your affine derived scheme will be given by like this, spec of A dot. So A dot is some CDGA. So what is changing? You have, of course, truncation functor. Therefore, somehow the old information is hidden in 0 level, basically, right? So you can go back by truncating your object into 0 level. And this is indeed a scheme. And the points are the same, basically, but the scheme structure is changed, okay? And fine, more or less, this is the idea. And therefore, when you define, for instance, so maybe a definition, when you define a notion like a stack, which means that this is a kind of a press stack, which is an assignment above by functor of points, right? And plus some local to global conditions. To encode this, we need to use homotopy theory as well. Okay, that's another story, of course. And more or less, this is the picture. Therefore, we will define all higher spaces, higher structure by using this functorial perspective. Okay, maybe final remark for this section. Actually, the remark is another way of interpreting the above diagram. The points of a scheme. So points of a scheme, remember this diagram. Oops, sorry. Points of a scheme forms a set. Therefore, points of a groupoid, points of a stack form a groupoid, not a set. It is local as a local model will be groupoid. So the points of a scheme form a set, but points of a stack form a groupoid. We will come to that. This will be very important. Okay. So fine. So actually that's all. And actually when we move, maybe a couple of words, when we move in this blue direction, actually you have more refined moduli data. This approach allows us to reorganize the moduli data so that actually we can deal with this representability problem. For instance, there exists a two-categorical version of the Yoneda embedding, which gives us the desired properties. There won't be any non-representability problem in this case. So two-categorical Yoneda embedding resolves the problem. Okay, fine. So the final part. How much time do I left? I just confused. When did we start?
We started around 5 past, so let's say you have about 20-25 minutes.
20-25. Oh, nice. Okay, fine. I don't know if you have any question, you can ask, of course. let's start with the final part. So the final part, we are going to combine ideas and the language we introduce in part 2 with the standard formulation in part 1. So let's see. So in part 1, basically what we observed, we just observed that, so defining a classical field theory, so defining a classical field theory, but maybe it's a bad abbreviation. This is abbreviation. It's not a conformal field theory. And defining a classical field theory actually corresponds to the study of the moduli space of solutions to Euler-Lagrange equation. So for me, studying classical field theory is actually just a study of the corresponding moduli space. And remember, now we have a new language to deal with problems in moduli theory. Now we will use this new language, and our slogan is, or the punchline, if you like, we really wish to define a classical field theory on M to be a sheaf of derived stacks on M. Okay, this is basically our goal, our motivation. Okay, so we combine this new algebraic machinery with this standard way of describing things introduced in part 1. So let's see, but how, right? Or why? Why are we doing this? The question is why? And we need to analyze, just revisit the critical locus discussion, right? I assume you remember this discussion, critical locus. And we have actually two obvious, more or less obvious problems here. The first problem is, of course, when you divide by this action, you have a problem, right? So this may be a bad quotient. Oops, bad quotient. And what does it mean? For instance, your action may be due to the non-freeness of the action, right? For instance, non-freeness of the action, right? So which means that you end up with an object which is not in your category, right? So your category is not big enough to somehow include the resulting object. Okay, so you have a problem. So this fails basically fails to live in the same category. Okay, this is one problem. Fine. Another problem here. This is about bad intersection. So let's see, what does this mean? Actually, if you look at carefully, this thing can be equivalently defined to be the intersection of the graph of ds with the zero section of the cotangent bundle inside the cotangent bundle. Okay, so the meaning is you have a fiber product. So this thing is just, so the critical S can be defined like this. So you have Fm, remember Fm was the space of fields. S defines on Fm, remember. So we really want to understand the critical locus of that function, right? And then Fm, so any space can be embedded into its, right, the cotangent bundle by using zero section. No problem here. And also we may discuss the graph of ds. The differential is the one form. Therefore, the intersection turns out to be your critical points. But the problem is, this thing is just a fiber product, right? So this part is just the fiber product. What is the problem? The existence, right? So the fiber products, I mean, not all categories admits, right, fiber products. So this is the problem. So for instance, in the category of manifolds, the fiber product turns out to be the intersection of a two manifold, but the intersection of a two manifold is not necessarily a manifold, right? So similar problem here. Therefore, actually, the whole problem can be reformulated by using this language. So, how can we, so non-existence problem here. Okay, so now we have, we just translate the problem by using this language. And the question is, how can we resolve those problems? Bad intersections and what is it? Bad quotients. Actually, this is why we have derived algebraic geometry. And the question is, how to avoid those problems? The answer is higher spaces, higher structures, and derived algebraic geometry. This is the reason why we need to use this language. Of course, you may ask, how? How is another story. I mean, there is a complicated theory. But the main motivation, or one of the main motivations behind the use of derived algebraic geometry, actually to find meaningful solutions to those problems, basically. This is the reason why we use those structures. Okay? Therefore, the derived algebraic geometry is a natural framework to discuss those topics. And let's see, for instance, Remark. Actually, when we go back, when we go back and revisit part one, remember the examples. I gave you an example of a, what was it? The gauge theory, for instance. Let's go back this example, and we will see that the stacks and the groupoids basically have already been there. So let's see. So in the gauge theory, stacks and groupoids were already there. Okay, let's see how. Just remember, in Chern-Simons example, if you like, in Chern-Simons example, remember we have connections, right? Connection one forms, I guess something like this, connection one forms, and the gauge transformations between them. Therefore, the phase space itself consists of two important information. It's not enough to specify points. You need to somehow keep track of gauge symmetries at the same time. Therefore, the phase space itself, the phase space is not modeled as a set. Remember, you have points, you have maps, so you have points actually, A prime, and at the same time you have gauge transformation. But remember, these are invertible, right? So maybe you have A double prime, this thing is invertible. So you have points together with arrows, which are all isomorphisms. What is this? This is just groupoids, right? So therefore, this thing is modeled as a groupoid. So groupoid is the right structure. Okay, so this is the idea. And the smooth structure on that space, now we call it higher space of fields, higher space of fields. Now we are going to use actually, I mean, the smooth structure on that higher space of fields, basically encoded by using the notion of a stack. Okay, therefore this leads us not just the space of fields, but this leads to define the stack of gauge fields. This is the natural framework. okay, which was already there actually, if you look at carefully. And actually, this is a little bit richer than the usual orbit space. Maybe Remark. This thing is richer than the usual orbit space. I mean, just quotient space, right? Orbit. Why? What is the difference? What is new here? Okay, now we just indicate which of the gauge fields are gauge equivalent. Okay, fine. This is actually what an orbit space does as well, no problem. But what is the extra information? Now we can basically keep track of how many ways they are gauge equivalent. Okay, so the extra stuff here, what is the extra stuff here? Now we just keep track of how many ways they are actually equivalent. Okay. And what else? Maybe a final remark is you can use these ideas to encode to study higher gauge theories. So this derived algebraic geometry language suitable for higher gauge theories. What does it mean? What does it mean? The meaning is now you have enough structure to introduce, for instance, gauge transformations between gauge transformations. Okay, now you ask for further information, gauge transformations of gauge transformations of gauge transformations. For instance, you have now infinite tower of equivalences, but we know a very natural framework to capture such an infinite tower of equivalences, right? So let me write it down. If, for instance, there exists a gauge transformation of gauge transformation, then actually the correct framework or natural framework will be two groupoids. If, for instance, there exists gauge transformations of gauge transformations of gauge transformations, and then the higher space of gauge fields is given by two groupoids. Okay, and the story goes like that. So, and then the natural framework will be, so the natural framework will be, we start with sets, but now we pass to groupoids. And depends on your theory, if you insist on higher symmetries, now we use two groupoids, and the story goes like this. And finally, we have infinite groupoids, or just simplicial sets. And the corresponding higher spaces will be, so if you have a set, okay, nothing new. So you have just space. The meaning is you have maybe a manifold, you have maybe a scheme, variety, whatever. But now, if you pass to such a framework, now you have stacks maybe, or you have higher stacks, n stacks, and story goes like this, and finally, infinite stacks. Okay, fine. So this is more or less the picture. I mean, and maybe a final example after this remark. Okay, maybe I'm not going to give that example. More or less, we understand the basic idea. So there are differences between a groupoid perspective and orbit space perspective. And as I said, those structures, some of them at least, have been already there. And so this makes sense to use such a language to capture higher symmetries or higher properties of the theory of interest, encode the aspects of the theory in a more foundational level. And more or less, this is the idea. Maybe, okay, so this is the story. Maybe I should stop here. Okay, thank you.
Thank you, İlker. So let's say Thank you.
Thanks. Thank you.
We can use reactions to clap. And do you have any questions from the from the audience? Dennis, do you have a question? Your microphone is unmuted. No questions.
Yeah, I have a question. For the gauge field theory, you are considering smooth manifolds like C infinity. But for the stacks, are you considering just in the algebraic framework or?
Sure, of course.
Fit into the...
Yeah, sure, of course. This is the one. This is another advantage of using this. For instance, now you can define even in non-smooth setup. For instance, in the smooth case, you have a tangent space, right? And maybe in non-smooth case, now you have a tangent complex, and then you can deal. For instance, you can define a symplectic structure. Remember the usual symplectic structure. The usual symplectic structure on a manifold, okay, you have a smooth structure, you have a tangent space. And what about derived stacks? So derived scheme, how can you define the corresponding simplicial structure or even Poisson structure? But now instead of a tangent space, now we are in non-smooth setup, you have a tangent complex or the cotangent complex. So by using those structure, you can generalize the usual geometric objects in this setup as well. So of course, this is one of the uses of derived algebraic geometry.
Thank you. Any other questions?
And maybe a short comment. All previous information about the usual structure are actually encoded in the 0 level. So when you truncate everything, you obtain a scheme. Okay, but now you have higher, for instance, higher cohomology groups. For instance, think about, I don't know, the example I gave you. So you have a symplectic manifold, for instance, here, right? So this thing is just a, what is this? This is a smooth section of, smooth section of that thing, right? T star X, blah, blah, right? But this is just a zero cohomology, right? But if you have higher cohomologies, in this setup, actually, you have non-trivial higher cohomologies as well, which captures further information. Okay?
Yeah, that makes sense.
Okay, any more questions or comments? If not, let's say thank you again to İlker.
You're welcome.
Clap. Now we can stop